All right. So I'm thinking about prediction in this talk. And this is an example of a prediction that we studied in a different master's project a few years ago, where a machine learner, let's say, is tasked with predicting whether a subject, perhaps a little older, will progress into Alzheimer's disease, say 4 years from now. And so what happens is that you have patients that come to memory clinics or see their primary care physician, and they show symptoms of cognitive decline, and then you might wonder, okay, will this develop into full-on Alzheimer's, or how will this person progress from now on? And so we wrote a paper together with some Alzheimer's researchers at Sahlgrenska and some master students here about this problem. And so in this problem, like in a lot of other problems, we were to some extent constrained by sample size. And this is always an issue when we're dealing with statistics, right? And you'll see a particular version of that today. But nevertheless, if we want to make this kind of prediction, a standard solution will be to try and estimate, say, the conditional expectation of the outcome, y, given the input variables x1. Or if we think more sort of traditional machine learner, we might want to minimize some risk. Although arguably it's a little bit strange to call this machine learning. This is just minimizing the square error in the example. And of course, regression has been doing this for a long time. But I'll be agnostic to what the class of functions is that we are minimizing over, at least for a little bit. I'll be agnostic to that. So we can imagine fitting some neural network to minimize expected risk or a linear regression or something else. So these are ways to learn prediction models, right? That was the task. And as I said, we have classical solutions to this. If you imagine these input variables x on the horizontal axis here, and we're trying to predict some outcome y. If that function y happens to be a linear function of the covariates here, maybe with some intercept and say Gaussian noise, then we know very well what to do. Our job is just to fit the slope of this line using, say, the OLS estimator or something like that. And we will, if we have a large enough sample, get a pretty good estimate of the conditional expectation y given x, which happens to be the slope of the line. Now, in this case, the empirical, or not the empirical, but the risk minimizer is equal to the conditional expectation, so we don't have to separate these two. I'll touch on that a little bit later. So this is an example, but generally speaking, in machine learning, we do this kind of thing all the time. We gather some data set of inputs and outputs, and we minimize an empirical risk. So we don't have access to the full distribution. Maybe it's a distribution over many or multivariate random variables, so we can't compute an expectation anyway. So instead, we minimize the empirical risk, which is just your average loss on the sample that you have, right? This is how we often pick hypotheses. There are many other learning principles in machine learning, but this is the sort of canonical one, if you like. Certainly the most widely used one. And if we gather enough training examples, then we can expect our empirical risk to be a pretty good estimate of the expected risk. And we can hope that also then our empirical risk minimizer, the hypothesis with the smallest average error, to be close to a minimizer of the expected risk as well. Okay, so we can do this thing. And we can use the hypothesis that we find to make predictions. And of course, at test time, when we use our model that we learned, we have access only to the information that's, the input for prediction. Say, and I've been calling that x1. We don't know what's going to happen in the future because that's what we're trying to predict. And so this will remain the setting for us at test time. But the point that I want to talk to you about today is that our situation might be different for the subjects that we have studied in our training sample. So at training time, we might have access to much more information because, okay, we have the baseline features. These will be the input to the prediction function that we have later on. We have collected the outcome, certainly, because we're doing supervised learning here at say, and we've waited long enough. So this exists. If we've waited 4 years to know the progression of Alzheimer's disease, probably we've measured something else along the way. Okay, so remember, at test time, I only have access to this. I want to predict 4 years into the future. But for my training subjects, 4 years have already happened. So maybe I saw them every 6 months. And this was the case in the Alzheimer's data set that we looked at. Subjects were, checked up on every 6 months or so with varying regularity, and ultimately, after 4 years or longer, we could sort of set the follow-up time for our predictions. This kind of structure is not limited to Alzheimer's disease. I'm not trying to give that impression. There are tons of examples outside of healthcare and inside of healthcare, which happens to be my own favorite domain. In healthcare, a very common one is predicting mortality after 30 days. So, for example, you can get to the intensive care unit, and the physicians, and well, everyone is hopeful that in 30 days you'll still be alive. But predicting 30-day mortality is a sort of common assessment of how well, or rather, counting 30-day mortality is a common way to assess whether a unit or a hospital is successful. But you can imagine predicting whether a user will churn, will leave your sort of software system in a year or in a month or something like that. You can imagine predicting the crop yields for a farm. All of these are tasks where you have some kind of fixed follow-up time in the future that you care about, but you can also conceivably collect information between your baseline and your follow-up. Interrupt me if you have any questions. I'll try to answer them. So everything in between here, I will call privileged information because it is only available at training time, and it's not related to what we're trying to predict. So it's not the target of our prediction. And then we will have our normal input and outcome variables as well. So you've noticed here that I have a special kind of privileged information. This is a time series, right? Generally speaking, privileged information could be anything that give access to a training time, but not a test time. But here we'll restrict ourselves to time series.
But do you make some assumptions on correlations between the baseline and the intermediate observed? Because the lifestyle we might have led up to the baseline might sort of carry on over into the intermediate.
Absolutely. So we'll make the assumption that this is the process causally, in the sense that x2, whatever happens here, is a function of this. Okay. So by implication, this y is only a function of the most recent time step and so on. So x1 cannot have an influence on the outcome other than through the privileged information. Yeah, that's the restriction we make here. Okay. Surprisingly, then, you might say, a lot of the time privileged information is discarded for no reason, really. But then I immediately contradict myself, because I say with seemingly good reason we can just discard it. What I mean is that you don't really need it if you have enough samples, if you have enough sequences, let's say. If you have enough samples of just the pairs x1 and y, you can learn a good prediction model. This conditional expectation, which I said was the risk minimizer, the best prediction model, that doesn't depend on the privileged information, right? So it sort of makes sense that if we're thinking standard supervised learning, we just remove everything that's in between. And again, given enough samples, we can do this. It just happens that it's often wasteful. So I'll show an example of that from the future of this presentation, which is that, yeah, privileged information can be super useful. There's a lot going on in this plot, so apologies for that. But what I'll point out is this green-gray mix of plots here. That's where the classical estimate would be, which is to throw away the privileged information, work only with the input-output samples. And these blue and red are privileged learners, so they make use of that information. And what you can see is like the best performance achieved by the classical estimate is achieved by the privileged learner for 60% fewer samples, which is how I'm counting whether a learner is efficient or not. So this is for the same hypothesis class. We're using the same architecture to learn this. These are with neural networks, we'll see later on. We have the same exact observation, not just the same number, but the same exact observations, except for one of them, we throw away the privileged information, for one of them we don't. Okay, so how can we show that this is going to happen? We have essentially two questions in this talk. One is, how do we best make use of the privileged information for learning? And the second is, can we prove that it will be useful? Not only empirically, but theoretically, can we prove that this will be useful? So we thought for a very long time about how to formalize this. The story of this problem is that I was a postdoc at MIT for a while, and I started talking about this kind of thing with my advisor. This was probably in 2018 or so. And because it was so common in healthcare data that you had all this data that you threw away. So we talked about it, we talked about it, we talked about it, and around came 2019, and I had to leave, and we didn't do anything with it. We couldn't think of a good formalization of this problem, or a good solution to it either. And then in 2020 or so, yeah, I thought about it some more, and I decided just take a master's student. We'll figure it out along the way. And so we spent a good 2 months again trying to formalize this problem or define this problem in a good way, and eventually we got to where we are in this talk. So I've been thinking about this for a long time, and hopefully it doesn't come across as too obvious, even though the solution is hopefully simple. All right. So what we decided to do is to say, okay, there's a data set. This data set is a number of samples of individuals, say, represented by the baseline characteristics, possibly privileged information, we'll get to that, and their outcomes. And we are considering learning algorithms, A, or script A, which operate on data sets. A learning algorithm takes a data set and spits out a hypothesis. And that hypothesis is a map from the first time step to the outcome. Okay, that's our task is to pick a good script A, a good algorithm, such that the hypothesis that it spits out is good. And I define here data set as being a set of these Z. So the Z would be either just X1 and Y if we're doing classical learning, or the entire sequence if we're doing privileged learning. All right. We will measure the quality by a learning algorithm by its expected risk. And the expectation is twofold here. So it will be an expectation over the data set that the algorithm was applied to, and an expectation over the samples that we might see in the future, meaning our standard generalization error or risk. So here we have an expectation of X1 and Y. We have our loss of our hypothesis H, which is the outcome, or the output rather, of the algorithm that we applied to the dataset D. So the dataset is random, the future test points are random, and we're taking expectations over both. So we are interested in efficient learners, as I said before, and we say that a learner is efficient or more efficient than something else if it, on average, outputs a hypothesis which is a better risk or a smaller risk using the same number of samples. Okay, so learning algorithms, we want to pick good ones. We consider two paradigms, as I said before. Classical learning, where we use only the input to the actual hypothesis that we use later, and the outcome that it's supposed to produce, so classical supervised learning. And then we have the privileged learners, which see the entire time series. We will denote these script AC and script AP, respectively. Classical and privileged. Classical and privileged. Okay. So, when can we prove that privileged information is useful? The way that we formalized this in the end was to say we want to show that the expected risk of a privileged learner is smaller than the expected risk of a classical learner on average over data sets and sample over test points.
But this, I mean, just formulating this involves an underlying model. I mean, you have to formalize that there is this the Markov model and all of that. In words.
To make progress, yes, but we're gonna do that. It's not required to ask a question. We just have to assume that there is a data generating distribution P. Are you with me?
Yeah, but this would be trivial because if you just throw out and then you get less than equal to.
Throw out.
If you just throw out all the privileged information, you have less than equal.
Ah, good. I should have a strict here. Thank you. There we go. So this is not always going to hold. There are counter examples to this that you can think about. So, I mean, first we could pick unsuitable algorithms. You can have a very stupid privileged learner and a very good classical learner. So we can't be agnostic to which algorithm is used. But we also can't be agnostic to what process we're studying, right? So there might be privileged information which is uninformative by definition. So where we have this kind of situation, you ask, like, how are things related? In this case, X1, which is the baseline, generates privileged information, which is completely unrelated to the outcome. And so this would only contribute noise in this case. It wouldn't help us make better predictions of why. And so we don't expect privileged learning to be useful in that setting. Of course, I can always revert to being a classical learner because in some sense they're subsets of each other. But yeah.
Something that ruled out this situation because you have this assumption that.
Yeah, exactly. I haven't officially made that assumption yet. That's just how I illustrated the problem. But yes, you're going to make that assumption. So the assumption that we make rules out this, exactly. Okay, so we can ask then, how would we prove something like this? And we could appeal to perhaps traditional learning theory. Maybe that has something to say. And just like the crash course of that, standard learning theory would try to give us a bound on the expected risk on new test points for a hypothesis H in terms of the training error, let's say, on a data set D, and something that measures how sort of much I spent my time fitting the data that I had in front of me. So essentially, this will be a function of the hypothesis class that you picked, the number of samples most crucially, and the certainty level by which you want this bound to hold. So far, I haven't said anything about how to use this, but hopefully you've all seen this kind of thing before, that eventually if we see enough n, if we see enough samples, we expect our empirical risk, or rather both our bound and our empirical risk to just converge to the true risk. So we will have a very tight guarantee for how well we will do on new samples if we have enough training samples. But the problem is that in the real world, yeah, go ahead.
The classical thing is the expectation on the D that you had.
No. In the classical thing, no. So here, H is any hypothesis, right? Whereas in our case, the H will depend on the data set. You're right. But you can, there is a version of this, a classical version of this too, where H is your empirical risk minimizer, and you basically only get this. You don't get the training. Okay, but in practice, oftentimes, this term is large because the complexity of your hypothesis class, or whatever way you measure how sensitive you are to data, that will be a very large term, and n might not be as large as you want it to be. So typically, these guarantees are fairly loose. Okay. Nevertheless, we can imagine using similar tools to give us the kind of result that we want, and people have studied this before, certainly. So Vapnik was he has driven a lot of statistical learning theory throughout the years, and he was also the first to propose this learning paradigm of learning using privileged information. And after a while, in 2010 or so, they analyzed a very, very particular setting of this, and basically proved that it is possible to have learning problems where a privileged learner can achieve a fast rate, which means that your error dictated as 1 over n, right? Your generalization error. Whereas a classical learner, a traditional empirical risk minimizer, will only have 1 over square root m, which would be the slow rate. So there will be a rate difference, which is a very notable thing to have, that you can decay that much quicker.
But how much extra information do you have to get that?
In this case, well, it depends what you mean by how much. In this case, they have 1 sample extra per each observation. So they have x, x star, and y, whereas the classical learner just has x and y.
Okay.
Yeah. So it's cool, but this x star, the privileged information, is picked in a very, very particular way. It's essentially giving you the errors that your learner would make if it only saw x. So it's a little bit fishy. But it's also it's only for a single data generating process that is very, very particular. So they define essentially a distribution on, say, like 4 points in R2 or something like that. Like it's that kind of special. Yeah.
Can you build some intuition of why there is smaller or equal to in the privileged case?
They just show that there's, I guess I could say equal here too. What I wanted to say here, I'm a little bit hand-wavy with the O notation. I want to just have a difference here. So this is bounded from above and below by a function that's in O1 over square root m. So I guess I could just say theta square root m, or 1 over square root m there. But this one is an upper bound only. So you can do better. But the other side of this is that the rate difference only kicks in when m is already large. So they have to assume that it's large enough, and that's not the kind of setting that we are interested in here. We want to make sure that we make use of privileged information when we are already sample bound, let's say. So the question is then, can we use this kind of thing to prove difference between these two? Well, not really if we have a fixed small n, which is the size of the data set, right? We can't really use it to prove what we want. And so generally speaking, I haven't been able to find an upper bound on the error of a privileged learner and a lower bound on the error of a classical learner, which is tight enough to separate them for small samples. And of course, again, we can compare asymptotic rates, but it's not really the right regime that we're interested in. Yeah.
Is it possible to get bounds for when we test for the case where we only use the previous information? We produce a x star. I mean, and
yeah.
Then we convey the x and use x star.
Good question, because x1 is needed for our input, right? So it's not entirely obvious that there is that you can learn the function that you need. So age, the function that our learner spits out, it's a function of x1. And in our case, they're kind of in the same space, but they don't have to be. So I would say not in general, no. But under assumptions, possibly. Yeah. All right. So we will need to make some more assumptions. At least that's what we did to make progress. And so we chose to study a linear case. Where, well, first our intuition, well, okay, I jumped the gun. First we wanted to say that we wanted to study classical and privileged learner which return hypotheses from the same class. So it's not that one is a neural net and the other is a linear regression. It didn't seem right to us. First of all, because we're then very clearly mixing bias and variance, and that's not what we were interested in the first place. But as we'll see later, maybe at some point we will have to mix them up. Nevertheless, we also restricted the data points at all time steps to live in the same space, RD. So this is connecting to what a little bit to you were asking there. It's mostly for simplicity. We could have them live in real spaces with a different dimension, but it allows us to define the data matrices in a neat way, and it's just easier. So bold x1 will be the n by d matrix of d features and m observations of those features. Yeah.
I mean, you can always have zeros in the.
Yeah. There are tons of ways to handle it. It's just simpler for our exposition in the papers and so on. Yeah, thank you. So now to the really strict assumption. We will assume that our data generating process is what we call an isotropic linear Gaussian chain. So it's a Markov model where each transition x1 to x2 is given by a linear function with some noise. So x equals 1 is given by xtat plus Gaussian noise. Simplest scenario you can imagine almost. The ultimate outcome here, y, will also be a linear function plus some other Gaussian noise. The only sort of not simplifying thing here is that we don't assume stationarity. So A1, A2, and so on, they're not the same matrix, at least. They can be arbitrary matrices. Well, not arbitrary, but they have to map to the right dimensions and so on. But yeah. Okay, so linear Gaussian. Let's see what we can do with that. Now, remember the first picture I showed you? There was a linear regression, and we said that the best prediction in that scenario is to have the conditional expectation, which is just equal to the slope of the line times the features. Yep.
Yep. You said it's not stationary, but isn't it not homogeneous?
I suppose we could call it that. Yeah.
I mean, I think the stationarity has a different connotation. It means to get much.
Yeah, you might be right there. Nobody has questioned this before.
Okay.
So maybe it's a community thing, but I'll accept it. Yeah. It's not, time series is not my main field, as you might have realized at this point. Thank you. So let's see, where are we? Okay, yeah, so we're in a linear regression setting, and in this case, because the whole chain is linear, that means that the best prediction of y from x1 from the first time step is also a linear function, because we have just got a composition of a bunch of linear functions. So if you wanted to redefine y in terms of just a function of x1, you can do it in the following way. You can define it, the expectation of y given x1 as just the product of all the matrices along the way. And then the noise term here will be this horrible expression, which turns out to be another Gaussian. It's just basically a weighted sum of Gaussian errors. So we are in this kind of scenario still, and y is a function of x1, it's Gaussian, but there's a difference now. The difference is that this line is given by multiple matrices, and the noise is partly explained by the variables in between, partly explained by the privileged information, because at every step here, I don't know if you can see very clearly, but at every step in the chain, there's a little epsilon t that gets added and accumulates in the noise of y.
Do you assume that you know the A's?
No, those are the, well,
Okay.
we'll get to that. So then in this kind of scenario, what's a reasonable classical learner? Well, we said that y was just a linear function of x1. So we're just going to do ordinary least squares, right? We'll just fit the best linear regression, predicting y directly from x1 in a single step. And this will be just this closed form expression, right? That you all know from I don't know when you learned that, high school, linear algebra. And as we also might remember from those courses, is that this OLS estimator is the minimum variance unbiased estimator. So if we restrict ourselves to unbiased estimators, we can't do better in terms of the risk. This will be the most efficient one that's unbiased. And I say that because I will have no regularization anywhere near this problem. And that's a big limitation of this work. But a regularized estimator might have smaller variance, but be biased. Okay. So what is a reasonable privileged learner then? Somebody asked about A's. Well, you just fit all the things. So the privileged learner will fit A1, it will fit A2, and all of the other A's, and beta. So each time step, you will have an OLS estimate, but now you're predicting a vector value thing. You're predicting the next feature based on the current ones. And the beta just takes the features at the last time step and predicts y. Your hypothesis that the linear spit out will be just the product of all of these things. You might ask, am I using the predictions of x2 to fit a2? Like I could fit this first and then predict these and then fit that. No, we're fitting them as if these pairs were completely independent of those pairs. That's how we're doing it here. And there's a very good reason for that, because if you fit this first and then you use those predictions to fit these, then you're not really using the, well, actually you can show that that turns out to be equivalent to the classical estimator. It's not obvious, but we can show that. Okay, so both of these estimators, the privileged and the classical one, will be linear regressions on x1. Both of them will return unbiased estimates of the quantity that we care about, which is the conditional expectation. And the only difference between them will be variance, which is a nice spot to be in, because then we know exactly what we should characterize. We want to show that somehow this thing has lower variance than this thing. Then privileged information has been useful. So that's what we did. We proved a little theorem. We assumed in this case that the Gaussian noise at every step was isotropic. So you have a diagonal thing, diagonal covariance matrix. But other than that, we also need that we need the what do you call it? We need the dimension to be smaller than n here. We're not studying the high dimensional setting yet. But in this kind of setting, then we can show that the privileged learner has a expected risk over data sets and samples, which is bounded by the risk of the classical learner minus something. That something is the expected variance of the classical learner, or the predictions of the classical learner, given a particular value of the privileged learner. So this is a little bit strange to look at maybe, but essentially over data sets, you will see different privileged estimates. You will get different predictions, right? Depending on what data set you have. If you condition, or say if you take one of those and then you condition on the value of that, there might still be some variance in which classical estimate you will get. And if you think about it, like a linear regression some line here. If you have noise on both sides of this line and you fit this line, you can just scale the noise and you get the same exact estimate. You'll get the same line. That's what this condition means here. But what we're saying is that for the data sets where we return a specific line using the privilege estimator, there might still be variance in what we get from the classical one. And so the gap between them is exactly this quantity. And since the variance is never negative, we at least have the less than or equal to based on this. And you can show, like in specific instances that this variance will be strictly larger than 0. But empirically, we really see this gap. Okay, so this is nice. This is the kind of thing we were looking for before. As long as this is greater than 0, this quantity, it can't be negative. Then we have a gap between the privileged and the classical learner. So privileged information is useful in this case.
But really, the natural thing you would think of that term there. I mean, it should
This?
be something.
No. Yes and no. It depends what you mean. Maybe you can.
Well, I don't know. I mean, it looked like it should be something related to this whole chain, and some. Something.
So where it comes from? The reason we put it in a risk way is just I've been talking about risk before. But in the original paper where we only study linear models, we are actually looking at the mean squared error in the parameter theta, which is the one-step prediction. And you can construct the one-step prediction from all of these by just multiplying them. So we're looking at the mean squared error in theta classical versus theta privilege. And so you will get the variance in that parameter, essentially. Now you can translate that to risk just by multiplying that by the input. I'm not sure if that's
the same. This.
It's the same exact form. You can just say instead. Let me see. Yeah, expectation over data sets and x. I guess you don't need x1 actually. You just expectation over data sets and then variance of classical given privilege. We can look at it later maybe. The main tool that we use to prove this is something called, it's not even on the, oh, here we go. A Rao-Blackwell technique. In a Rao-Blackwell technique, you prove that if you can compute the expectation of an estimator given a sufficient statistic, that thing itself will be more efficient than the estimator you started with. So if this is a sufficient statistic of your data, this is some estimator, I can compute this expectation. That thing is a better estimator than theta c. And in our case, it turns out that a sufficient statistic for this is just all of the privilege parameter estimates. And the conditional expectation here will be equal to the product of all those. It wasn't obvious to us when we started. So the conditional expectation of the classical estimate given the privileged estimate is just the privileged estimate. Okay, and then you can kind of realize why the variance term is what separates these two. Like again, we have this line, right? And we say that this is my privileged estimate. I've conditioned on it. It's this stuff here. It's a line. The expectation of the classical estimate for such instances is the same line. It's the same thing. Anything that separates them will just be variance.
What you're effectively doing is you're reducing the degrees of freedom in the system.
Yeah, you can say that.
Saying that there are, originally have a random walk with every possible thing, and then you say there are these kind of paths that have, that reduces the degrees of freedom.
Yes, so that's how we conceptualize it first. I don't know if I want to go back all the way, maybe. Yeah, we were thinking of this problem as when we condition on the privileged information, we reduce the hypothesis class, we reduce the number of feasible solutions or solutions that are consistent with the data because we have more things to be consistent with.
Yeah.
The proof is much more like direct than that, actually. We just show essentially through a symmetry argument that our this classical parameter is Gaussian around the parameter that we get from the privileged line. So it's just algebra. But the intuition is exactly what you said. Okay, so the takeaways from this is that, well, first of all, the result is independent of sample size. Maybe I didn't say that, but well, so this result holds for a fixed size data set, a random data set of fixed size, but that size could be anything. It could be 2, it could be 1 billion, it doesn't matter. well, I guess it couldn't be 2 if your dimension is too high, but we need both estimators to be feasible. Okay. Now, the way it works, I would say, is that part of the variance in the outcome that we're trying to fit is explained by the privileged information, because yeah, it's itself noisy, and once we condition on it, we know implicitly what those noise variables were, so we can remove part of that noise. One thing to note, though, is that we're now, with the privileged learner, we're fitting t-1 times d squared plus d parameters. So d squared because we have a bunch of matrices, and we have t-1 times that, and then we have just a prediction at the end. Whereas the classical learner is only fitting d parameters, and still we're getting a variance improvement.
That was this is very unintuitive. You're fitting a much.
Yes, much more parameters. We also have more samples, but we only have t-1 extra samples, right? We have those extra privileged points, but it's because of the dependent structure, I imagine, that this works out. It's still unintuitive to me, but well, it works.
Just as long as you have that condition and expectation result, it works out.
Yes, exactly. It does, but it's still, it feels odd. So, by the way, something that a huge limitation, maybe I'll get to that a little bit. It would make much more sense if we had stationarity or homogeneity, right? If we had the same matrix at every time step, then we expect, okay, we have so many samples to learn that same matrix with, but we have no result for that setting. We actually only have it in the non-homogeneous setting.
I don't understand anything of the criticality, but since you know there is this kind of reduction in degrees of freedom, are these t-1 d squared plus d parameters, are they independent?
Yes, I mean, in the sense that they don't have, yeah, they don't have to have anything to do with each other. No.
But there must be some sort of, I mean, for the linear, you can see that you're applying the linear transformation multiple times. You are basically testing pairs or along the, that's how I understand it anyway. So there has to be some sort of, the spectrum of these matrices has to have eigenvalues that are strictly, in order for the variance to go down, the spectrum has the largest eigenvalue has to be.
I mean, the theorem works even if you have an unstable system. It doesn't, there's no restriction on the matrices.
Product in the end.
Yeah, I think the real reason is the product. Like the actual function that we're fitting is just a, we just need the parameters to express the function, right? So effectively, we only have these things to fit. Now, the actual number of parameters, I guess, doesn't matter so much. Yeah, so you could say, I mean, it's over-parameterized, but in a different sense than we're used to, perhaps. Okay, I'm gonna have to move on because I have so many things I want to talk about. So we can do this in practice, right? So we have here an example of, well, predicting Alzheimer's disease. We have a continuous version where we predict a cognitive test score called AMC, and one where we predict the diagnosis, so Alzheimer's or not. And the blue line here is a classical estimator. The red line is the privileged estimator. And we see in R squared, we're doing better. In AUC and the classification, we're doing better as well. The black line here is where we do actually assume stationarity or homogeneity, I should say that, meaning we fit just a single matrix and we do better as well.
It's synthetic data.
No, this is real data. And so we have no reason to believe that this model holds at all, but we're doing quite a bit better here. You should notice though, I mean, the R squared pretty low. There's a lot of unexplained variance here. And the number of samples even smaller. We have 200 samples at the very right-hand side here, but that's the regime that we're talking about here. This is a fairly small problem.
Your real data, it must be the case that this A is the same. I mean, some reason why this.
We'll see maybe examples later. It's certainly not the case that homogeneity always does better, or assuming that does better. So we have a traffic prediction task, for example, where that did worse.
Yeah,
different data. Yeah, for sure. I think in this case, it's more that there's only a very simple signal that we're picking up. I don't think this example is all that interesting, actually, in the sense of the function that we're trying to learn. Like we've found quite a few things at this task, and we've never found anything really outstanding in terms of prediction performance. Nevertheless,
If you did a
for the best linear approximation, yeah.
If you do a synthetic data set and we just construct it with the same A.
Oh, we've done that. Yeah, yeah.
Obviously, the A thing will be.
Oh,
better.
sure, yeah. We've done that also.
Synthetic data set with the A's are different. I'm sure that the A's
Yes,
are.
exactly. We've done those are in the paper. The synthetic data. Yeah, you're right. Okay, let's move on. So the biggest limitation here, obviously, at this point, is that we've assumed linear Gaussianity. It seemed that we could do better in with privileged information also empirically when the thing is not linear Gaussian, but we can't guarantee that. And one thing to point out here is that the bias that we accrue for the privileged learner might be much worse than the classical if the true thing is not linear, because then we're fitting a bunch of linear approximation and combining them as opposed to just a single linear approximation. So when we combine the linear approximations, we no longer have a guarantee that we will find the optimal linear approximation to a nonlinear function. So that's the penalty we pay here. Yep.
Assuming we don't care about bias,
yep,
then is it possible to come up with some kind of privileged information formulation which reduces, for example, variance and more?
Interesting. We thought about, for example, regularization for this. I'm not sure if I mentioned here, but I don't know if that's what you're.
For example, in very high dimensions,
yeah,
there are these time estimators, for example,
yeah,
that they say bias estimation is better than an unbiased. Unbiased estimation. So perhaps in very high dimensional setting, we may not care about bias, but we just want to use the previous information to reduce the.
Yeah, empirically that's true. We tried it out. As I said before, we explored for a very long time just random things, and yeah, adding a ridge penalty in a very high dimensional setting helps also with privileged information. But we don't have any proof of that. It's just empirical. The other thing is, of course, we're basing our estimation on OLS, and maybe this is not, I mean, maybe this isn't worse than the first one on its face, but we actually make use of the explicit form of the estimate in our proof, right? So it's hard to generalize because we can't just have a risk minimizer. We actually need one where we can characterize the predictions made by the classical learner conditioned on what the privileged learner would have done. So it's a kind of a niche situation. We have a Markov assumption on the variables. I don't think we actually need that. We just need a DAG, a directed acyclic graph on the variables, and we need to know what is apparent of what. I think that the generalization follows. But we also haven't characterized really what the gap between them are in terms of magnitude. You would have to look at, it's harder than it seems. We're doing linear Gaussian things, so it seems like you can compute the variance for each of the OLS estimates, but the combination of them makes it tricky to characterize the gap. I'm sure you can do something there. Now, what I actually wanted to talk about today, or at least I wanted to talk about this also, is the nonlinear case. So I just said this is hard to generalize because we know the form of linear or of OLS estimates and so on. And so that's still true. And what's worse, we didn't really know at the start. So this was work in the spring with Bastian Jung, who was the master student with me. We didn't really know where to start with the nonlinear case because things can be nonlinear in so many ways. So before I mentioned, we had this intuition that the privileged learner and the classical learner should return comparable functions. They should be from the same class. But if you have, let's say, nonlinear transitions like this, it's not obvious that if you start with G1 from some hypothesis class and you G2 and all of these, they belong to the same hypothesis class. Now you compare that to something that predicts Y from just X1. It's not always the case that that comes from the same class, the best approximation there. So we would want some way of combining, you know, if we wanted to use the same intuition as before, something that combines estimate of these transitions in a way that returns something that is comparable to what you would have got if you did a one-step prediction. So this didn't make sense to us for a while. So what I'm asking is, what is a classical script AC to match a privilege? Oh, AP, it should be over there. And vice versa. There we go. All right, yeah. What we settled on was this. If up there you see the old case, this is the linear case, everything is observed, X1, X2, and so on. All of those are observed at training time. But for our nonlinear generalization, we looked at a latent case, a latent system where there are some variables Z1 through ZT. Those are unobserved to us. but they behave as a system we knew from before.
Yeah. The state space model or?
Yes. So they're continuous states, but it's a linear state space model, let's say. Yeah. And we don't know them. But the top part here, Z1 through Y, it's exactly the same system I had before. It's linear Gaussian, isotropic noise, all that stuff. Now, what we actually observe are these X1 through XT. They are some nonlinear transformation of Z1, which in this case is without noise. I don't think that's a big restriction, actually, because you could just add a dimension here, which represents the noise, and then transform it. But so there's some function C, which has a left inverse. We don't require it to be 1-to-1, but it has a left inverse phi, which gets us from X1 to Z. We don't know this, we don't know phi, and we don't know the A's and betas. Okay. So in this case, what happens to classical and privileged learners and so on? Well, now we can write our conditional expectation of y in x1 as a linear function of phi. Like phi is applied to x1. I get to z1, and then the rest is linear, just like before. So I have a linear transformation or linear prediction, let's say, of a nonlinear transform. And I can also write it in terms of this decomposition that we did before. A1 through AT, beta, take the product of all of those and then apply that to phi. So if you knew phi, it's the same as before. We're just operating in phi space now. So a classical estimator can be we just need to estimate phi somehow, and we need to estimate theta, the prediction somehow. And the privileged learner is exactly the same as before, but now in phi space.
But here seems like this, the invertibility is a very strong assumption. You're just saying that because you're really assuming that from Z to X and so on is completely invertible. It's not normally what you would assume.
Yeah.
You observe some partial thing.
Yeah. Good point. So but it's in the right direction, I think. We just need to be able to recover Z from X, not the other way around. So if Z is a very simple thing, say, we'll see an example later where Z is like 2 dimensions, a 2-dimensional real variable, and then X1 is an image of a clock face, say. So X1 is super complicated, but it's representing those 2 dimensions by the sort of, what do you call it? The hands of the clock. And that satisfies these conditions. It's not going to always be the case.
It's natural to assume that it's a hidden market model here.
Yeah. I mean, it is.
It's essentially a hidden Markov model, except they're using a nonlinear thing.
Yeah, for sure. I mean, it is I would call it an example of a hidden Markov model. It's just nonlinear. Yeah.
If there's randomness to the themselves.
That's also true. Yeah, you could that would be typical of a hidden Markov model. Yeah.
So this also helps to reduce the dimension of and dimension function.
Yeah, so actually, good point. I mean, we don't actually make use of that, but you're right. And the reason we don't make use of it is that it applies to both the privileged and the classical learner the same. Like the phi sort of reduces the dimension for both of them. Yeah.
So maybe I'm jumping over there, but
No, that's good.
you only need phi for the training.
I only need phi for training. We don't. Phi is not known to us yet.
You assume that function is homogeneous, and you need to estimate it, right?
So yeah, we need to get it somehow. I'll cheat a little bit later, but don't worry about that for now. At prediction time, we will need phi also because we need to predict. Well, we make this kind of prediction. So like we look at x1. I want to predict y. So the true model uses phi and then a linear prediction. Yeah. Okay. Now, what's the cheapest thing we can get? Well, the cheapest thing is to assume that phi is known, because then same exact story as before follows. Meaning we're just now doing linear regression in phi space instead of the original space. Now we didn't do much more than that, unfortunately, but we proved that it's enough to know phi up to a linear transform. So you don't have to know it exactly, but you can have a linear invariance in what you know to be the true phi. We would have liked to say more, but that's where we ended up. So if you know phi up to linear transformation, then you can get exactly the same result as before. why that's still slightly interesting is twofold, I guess. One is that, well, why it's mostly interesting to me is that there are latent variable modeling techniques that allow you to identify exactly that, allow you to learn a representation of your data, which is consistent with a true latent variable up to linear transform. And nonlinear ICA, independent component analysis, is an example of that. So we could conceivably combine those two, although we don't do that in this work. The other thing is that we don't actually need to know an explicit representation of phi. It's enough to know it through a kernel. So we can have a kernel which is just a product in the phi space, and it's enough to know the kernel. We don't have to have an explicit representation of the phi function.
That's great. But the formula you seem like you needed explicit.
I know, but I don't show it on the slides here, but basically you can convert your estimators. So instead you're taking products of matrices, you take products of kernel matrices applied on the x's, and you use that in your you use that to get your linear parameter. Like you use that at training time to do the OLS estimation, and then you use the parameter that you get for the prediction. So let's see, at test time you just need the kernel in x1, I think. Yeah, I forget. But we have a result for that as well. Okay, I'm gonna have to speed up a little bit. So if you don't, okay, I said I was cheating here in the sense that I assume I already know phi a little bit. And we do something to say that you can do something even when phi is completely unknown. So what we do is to use something called random feature representations. So if we don't have phi, we can at least show that random feature embeddings lead to consistent learning for both the classical and privileged learner. So a random feature is just, let's say phi hat, which is a nonlinearity applied to a random projection of x. So think of W as a big Gaussian matrix, like independently drawn Gaussian variables in a matrix, multiply that with your data matrix X, and you apply a nonlinearity phi. That's your representation now, and then you fit a linear model on top of that. So you can think like the easiest thing to imagine, I think, is a randomly initialized single layer neural network. That's an example. And in this case, we used value features on that single hidden layer. You train the last layer, but not the hidden layer. Okay, so if we use random features, we can show that both the classical learner and the privileged learner will converge to the true thing that we're looking for if given enough samples. So that gives us at least some idea that both using random features in privileged learning is sensible. But of course, I've told you before that this is not the setting that we care about. We want to do more than this. This is the asymptotic regime where we want to show something in finite samples. So yeah, since I'm going to run out of time, the biggest open question for us is what happens in the finite regime when we have random features. We have started to characterize the bias that you get from the approximation of random features. Basically, what happens is that you need more and more random features, like a bigger and bigger hidden layer in your neural net, to get consistency. But so we've started to characterize the bias, but the problem with the privileged learner is that it all compounds in a horrible way. So it's a little bit hard to characterize. One cool thing that we realized when we looked at the kernel version of this, is that you can prove that if you have more dimensions than features in your more dimensions than data points in your representation, then the privileged learner and the classical learner are equivalent. And that's also not obvious to see, but it has to do with the OLS estimation again, that you have a bunch of matrix multiplications that just cancel each other. So in the regime where the covariance matrix is invertible, or is it the other one? Which one is usually invertible? The covariance matrix, right? Yeah, so when X transpose instead of X transpose X, when that's invertible, then the two estimators become equivalent. And so that's in this regime over here where we have more features than we have data points. In this regime where the features are fewer than the data points, then we have a benefit of privileged information. So that was interesting to us. Again, regularization would be super interesting, but we don't have results for that.
That's consistent with what one might expect in that high dimensional setting. There is information such as.
It's not true with regularization. I'll tell you that. Yeah. So for random features, for example, there are results in that regime, but we haven't looked into it yet. So for random features, we see that we get benefits both of being nonlinear. So remember the feature embedding is random projection plus nonlinearity, or nonlinearity applied to that. So we get a benefit of nonlinearity because we compare this gray line, which is the best linear learner, to these two, which are random value features. In this example, I show this to illustrate compounding bias, because here the black line is a privileged linear learner applied to nonlinear data, and the gray one is a classical linear learner. So the gray one is actually doing better here, and that's for the reason I said before, that we're fitting a bunch of linear functions to a nonlinear system, and we get compounding bias. Whereas for the nonlinear functions, which are the blue and the red here, the privileged ones are above the classical ones for both.
So this is on synthetic data, right?
This is on synthetic data, but we see the same thing for other data. Actually, we don't see the black and gray reversed. We have to fight a little bit to do that poorly.
Okay.
Yeah, so for example, the traffic prediction task I mentioned before, you still do better with a linear. You just plateau much quicker than the nonlinear ones. So they keep increasing.
And the data generating process that you generate the synthetic data is consistent with the random predictions.
They're consistent with the Z sort of X thing, yeah. We can of course do neural net stuff too. So instead of doing random feature embeddings, we can learn a representation. So a classical representation learning would just take your X1, produce some Z, and then predict Y. This part is nonlinear, this part is linear. So it's doing this kind of prediction that I illustrated before. And then we can incorporate privileged information into this by mapping not only X1 to some Z space, but also all of the other X's using the same representation function that we have. So B here is the same throughout. And then we have a number of different variants for that. The one that most closely corresponds to the linear version is really bad. So that one just predicts the next Z in phi space, next Z, next Z, next Z, and then at the end predicts beta. But that means you spend most of your time learning a representation which is good in this transition, which you don't really care about. You just care about predicting Y in the end. So maybe you could do something with weighting there, but we found it much better to just map everyone to the same, to Z using the same function and predict Y from every time step instead. And this works too. So this was the figure I showed you early on, where you got a like 60% decrease in the number of samples we needed to reach the best point of the classical learner. This was the data where we had essentially clock phases. They're like, these are images that are the input at different time steps, and they're representing some two-dimensional latent variable, basically. Yeah, so we get something there. We also get that the latent variable is better recovered by the privileged learners. So here we have a measure of how well we recovered the latent variable. Here we have the prediction performance. And what we see is that, okay, some of the classical ones achieve pretty high prediction performance, but they're nowhere near as good as at predicting or recovering the latent variable. We can see that here also, although it's a little bit incomplete, but these are the latent variables which were originally this rainbow plot here. They're not so well recovered by the classical learner, but okay, separated by the privileged one. All right, good. We needed a yawn because I'm almost out of time. There are tons of open questions. We don't have any results for biased cases, and we really want them. Regularization is one. Random features with finite number of features is another one. We don't know what to do if we have a general non-parametric estimation. We know something. We know how to do it with kernels, but the problem is if you have a universal kernel like a Gaussian kernel, that's in the D larger than M regime, so you get no benefit. For RBF kernel, we can show that a privileged learner of our kind is useless. It doesn't do better than classical. Doing stuff beyond chain graphs would be nice, and also have other kinds of proof techniques than raw black hole because it's so finicky. Just a parting words. Don't throw away your privileged information. I know a lot of you are working with time series data, and maybe you are in the same boat as me. You just didn't know what to do with it before. But yeah, there are at least 3 ways we know how to deal with it now: the linear, the kernel, and the random feature and the neural net. So it could be useful. Again, I just want to highlight that this was work done with mostly master students. So Bastian was my student in the spring, and then Rickard and Martin were the year before. Rickard is a student a PhD student in Delft now. So I'm very grateful to them, of course. We involved my old MIT lab in this as well. But yeah, that's all for me. Thanks for listening.